All at once, every single one of NASA's Mars missions, from Perseverance and Curiosity to their orbiters circling overhead, went dark. No data, no weather reports, not even a blip from Jezero crater. It happened the moment the Interstellar Wanderer 3I/Atlas flared in Mars's sky, cutting through its orbital path. Space agencies call this a temporary anomaly, but the odds of total silence are astronomical. Has an outsider really managed to sever humanity's lifeline to an entire planet? What they're not telling us about 3I/Atlas's approach could redefine our place in the universe, and the evidence is mounting. How did all of Mars go silent, and what, if anything, will break that silence now? At 14:07 UTC, Deep Space Network consoles in California, Madrid, and Canberra flagged the same alert. All Mars data streams flatlined. No weather packets from Perseverance, no methane updates from Curiosity, not even a ping from Ingenuity's backup beacon. The shift supervisor at Goldstone scanned the logs. Every scheduled downlink from Jezero and Gale registered 0 packets. Engineers reran the handshake protocols, switched antennas, cycled frequencies. Nothing. Internal chat lit up with terse messages. Mars assets dark. No relay from MRO. TGO silent. Within 10 minutes, the room filled with the sound of automated alarms, each one tied to a different mission, each one confirming the blackout wasn't local. On-console staff cross-checked DSN shift logs for solar interference, but the sun sat well clear of the Mars-Earth line. No scheduled maintenance, no known outages. The last Perseverance packet time-stamped 13:59 UTC. After that, every graph on the console dropped to baseline. JPL's Comdesk issued a Level 3 anomaly notice. Operators ran diagnostic loops through the night. 12 cycles, all silent. The phrase "all assets dark" appeared in the internal log at 14:17 UTC, barely 10 minutes after the first missed window. By then, the blackout order was in place. No one in the control room had ever seen every Mars mission go silent in unison. The sense of isolation settled in, heavy and immediate, as if a switch had been thrown on an entire planet. Mars for decades has been a world mapped and monitored by a fleet of robotic explorers. Perseverance, the flagship rover in Jezero crater, is responsible for collecting rock samples and searching for ancient life. Its cache holds the most promising clues to Mars's past, waiting for a return mission. Curiosity, still active in Gale crater, tracks methane levels, an elusive signal that could hint at biological activity below the surface. Ingenuity, a helicopter no bigger than a drone, pushes the limits of flight in the thin Martian air, scouting ahead and testing hardware for future missions. Above them, orbiters serve as both scientists and lifelines. Maven circles high to study the upper atmosphere, measuring how solar wind strips away Martian air. Trace Gas Orbiter searches for faint signs of methane, cross-checking ground readings and relaying commands. Mars Reconnaissance Orbiter, the workhorse, delivers high-resolution images and acts as the main communications relay for surface assets. Each mission transmits a steady stream of data, weather reports, dust storm alerts, atmospheric readings, and gigabytes of imagery. This network rarely falters, even during dust storms or minor equipment failures. Simultaneous silence across all channels is statistically unprecedented. With the blackout, Earth loses not only environmental monitoring but also the ability to respond to hazards. Sample caches, methane spikes, dust devils, and seasonal changes all go unrecorded. The scientific cost is immediate and severe. Mars's robotic colony has gone dark, and every unanswered ping is another missed discovery. Every bit of data from Mars follows a relay chain built for redundancy. Surface missions, rovers like Perseverance and Curiosity, even the Ingenuity helicopter, rarely transmit directly to Earth. Instead, they beam their findings skyward to orbiters such as the Mars Reconnaissance Orbiter and Trace Gas Orbiter. These orbiters act as both scientific outposts and communication hubs, collecting packets from the ground and queuing them for high-gain transmission. The next link is the Deep Space Network, or DSN, a trio of massive radio antenna complexes spaced almost evenly around the globe. Goldstone in California, Madrid in Spain, and Canberra in Australia. This global array ensures that at least one site can see Mars at any given time, round the clock. Each DSN station cycles through scheduled contacts, locking onto the signal with precision timing. Data travels across millions of kilometers, bouncing from Mars orbiters to these dishes, then through fiber networks to mission control. Known weak spots in this system are well documented. Solar conjunction, when the Sun passes directly between Mars and Earth, floods the radio path with interference. These blackouts are predicted years in advance and logged in mission calendars. Dust storms on Mars can choke off solar panels, but they seldom strike every asset at once, and even then, orbiters with nuclear power or robust batteries keep transmitting. DSN outages are rare and, when they occur, affect all deep space traffic, not just Mars. During the current blackout, no such events were present. The Sun was well clear of the Mars-Earth line, DSN logs showed no scheduled downtime, and other missions, lunar orbiters, probes at Jupiter, continued reporting without interruption. For every mission on Mars to fall silent together, the odds are vanishingly small. The architecture is designed to prevent exactly this kind of total loss. 3I/Atlas, catalogued as C/2025N1, entered the astronomical record as only the third object confirmed to cross into our solar system from interstellar space. Its discovery in July 2025 triggered a global surge in telescope time, not just for its rarity, but for its baffling behavior. Unlike Oumuamua, which tumbled through without a coma, or Borisov, which followed a classic cometary arc, Atlas broke the mold from the start. Observatories first picked it up at 6.4 astronomical units, beyond Jupiter, already trailing a luminous emerald green coma. Standard models predict comets only begin to shed gas and dust as they near the Sun, driven by solar heating. Atlas was active far earlier, with photometric measurements registering surges in brightness that defied the expected curve. Its green glow, captured in stacked images from Pan-STARRS and Atlas survey arrays, pointed to abundant diatomic carbon, C2, excited to emission at a distance where solar flux should be too weak. Each week, the comet's light curve showed abrupt, irregular jumps, as if something inside was venting energy in unpredictable bursts. These weren't the slow, steady brightening events typical of long-period comets. Instead, Atlas's outbursts arrived without warning, sometimes doubling its apparent magnitude overnight, then fading just as quickly. Astronomers at the Minor Planet Center logged each anomaly, debating whether rotational jets, episodic fragmentation, or some unknown mechanism could explain the data. By late August, the object's trajectory was calculated to pass just 30 million kilometers from Mars, closer than any prior interstellar visitor to a planet with active observers. The timing was uncanny, with Mars orbiters and surface missions poised to capture the event and ground-based teams racing to refine their models. The scientific community found itself confronting an object that refused to fit established categories. Every new data point raised fresh questions. Was Atlas's early activity a sign of volatile, rich ice, or something more exotic? The comet's unpredictable behavior made it a prime target for intensive study, setting the stage for a wave of speculation about what might happen as it swept through Mars's orbital corridor. Day 1 began with a missed check-in from Perseverance. No weather packet, no status update, just a blank entry in the Deep Space Network log. Mission operations flagged it as a possible relay hiccup, but within the hour, Curiosity's scheduled transmission also failed to appear. By the afternoon, Ingenuity's beacon missed its backup ping. Engineers at the Jet Propulsion Laboratory and the European Space Operations Center in Darmstadt compared logs, searching for overlap. The anomaly widened overnight. MAVEN's atmospheric data, usually clockwork, arrived in fragments, timestamps out of order, with telemetry gaps stretching for minutes. Mars Reconnaissance Orbiter returned its daily image batch, but more than half the files were unreadable, 60% corrupted, with headers missing or replaced by strings of zeros. Trace Gas Orbiter's methane readings, vital for cross-checking ground events, trickled in with entire spectra blanked out. By day 2, the pattern was unmistakable. Deep Space Network controllers in Madrid logged repeated loss-of-lock events. Signal strength flickered, then dropped below threshold. Each attempt to re-establish contact produced only static. The European Space Agency's operations lead, Dr. Lise Moreau, convened a cross-agency call, reporting that Trace Gas Orbiter's partial data loss was now critical. She noted that lunar and deep space missions continued to report normally, isolating the blackout to Mars's corridor. The escalation spread to private sector partners as SpaceX flagged lost handshake attempts with Mars relay satellites, prompting a stand-down order for Starship launch teams. By the start of Day 3, every Mars asset was silent. No environmental alerts, no surface imagery, no orbital relays. The blackout was total. Internal chat logs from both NASA and the European Space Agency show growing frustration. Engineers cycled through frequency bands, swapped out ground hardware, and even attempted blind uplinks, but nothing broke the silence. Each failed attempt deepened the suspicion that this was more than a technical failure. As 3I Atlas brightened in the Martian sky, the blackout's timing drew scrutiny. The correlation was too strong to ignore, fueling heated debate inside agency teleconferences about the possibility of external interference. A pattern began to surface outside official channels. Amateur astronomers working with backyard telescopes and automated photometry rigs started sharing their observations on public forums. One of them, Rajiv Menon, a software engineer in Pune, noticed something odd in the light curve data from 3PON-I/Atlas. Every 7.8 hours, the comet's brightness jumped in a sharp, well-defined pulse, far too regular to match the chaotic outbursts of ordinary comets. Menon posted his findings, complete with time-stamped plots, to an astronomy Discord server. Within days, other observers from Arizona, Chile, and New South Wales confirmed the cadence. The pulses appeared globally synchronized, each one recorded within minutes of the next, regardless of hemisphere or equipment. The timing was uncanny. Cross-referencing the pulse intervals with Mars communication logs, Menon found that every blackout event, every loss of signal from the Mars fleet, began within 5 minutes of a recorded brightness surge from 3PON-I/Atlas. The overlap was not perfect, but the alignment was close enough to raise eyebrows among professional astronomers. Data from the Las Cumbres Observatory Network, usually reserved for supernova follow-ups, showed the same rhythmic peaks in their archival photometry. Speculation ran wild. Some argued for a natural explanation, perhaps a rotating jet on the comet's surface blasting gas and dust at regular intervals. Others wondered aloud if the pulses were something more, a form of energy emission strong enough to swamp the narrow radio bands used by Mars orbiters and ground assets. No one could point to a known mechanism that would allow a comet, even an interstellar one, to jam signals across millions of kilometers. Yet the cadence held. Each blackout window coincided with a photometric spike, as if Mars and 3I/Atlas were locked in a silent, invisible exchange. The debate spilled into agency Slack channels and late-night teleconferences, with no consensus in sight. Rubin Observatory's nightly survey logs flagged an anomaly just after the Mars blackout. In 3 consecutive exposures, faint points of light appeared near 3I/Atlas, too bright for background stars, too steady for dust. Over the next 48 hours, these objects tracked the comet's motion, never drifting apart. Astrometry teams, working through internal Slack channels, measured the spacing. Each object maintained a fixed position, forming a near-perfect triangle. No known comet fragments behave this way. Natural debris scatters, disperses, or fades. These held formation, frame after frame. The initial hypothesis, chance alignment with background sources, failed under repeated checks. Cross-matched catalogues showed no matching stars, no known asteroids, nothing to explain the pattern. The data embargo came quickly. Senior staff paused public alerts, citing the need for further review. In private threads, one mission scientist wrote, "If these are fragments, they're not acting like any we've tracked before." The formation's persistence, 48 hours, no measurable drift, pushed the conversation into uncomfortable territory. Were these natural companions, or something engineered to travel alongside an interstellar object? The question circulated quietly among those with access to the raw images. For now, the triangle held, silent and unexplained, shadowing 3I/Atlas as it swept closer to Mars. Mars is a planet on edge, its atmosphere thin and constantly leaking to space. For years, MAVEN has measured this loss, sometimes as little as 20 grams per second, sometimes surging toward 100 when solar storms strike. Even during quiet periods, the escape never stops. Every hour without MAVEN's plasma readings leaves scientists blind to subtle changes. If a solar wind spike hits now, there's no warning. The last available data showed the upper atmosphere fluctuating, but the blackout cut off any chance to track new events in real time. Curiosity's methane logs are another casualty. Methane on Mars is rare and mysterious, hinting at possible biological or geological sources. Spikes have been recorded before, brief sharp increases that fade before orbiters can confirm them. With Curiosity silent and the trace gas orbiter offline, there's no way to cross-check a sudden burst. Any new anomaly, whether from subsurface chemistry or an unexpected plume, will go unrecorded. Dust storm season is approaching too. Without regular weather reports, ground teams can't predict when rovers might be trapped or forced into hibernation. The scientific loss compounds with every missing hour. As Dr. Elena Ramirez, Curiosity's project scientist, put it, "It's like flying blind through a storm. Every unanswered question grows larger the longer the silence lasts." Official statements arrived within hours, each one carefully worded. NASA's public affairs officer repeated, "We're investigating a temporary anomaly in the Mars network. No evidence points to external interference." ESA's press desk echoed the line, attributing the blackout to a possible engineering issue. Yet, the technical logs told a different story. Deep Space Network records showed uninterrupted performance, no hardware failures, no scheduled downtime, and no unexplained outages in the antenna arrays at Goldstone, Madrid, or Canberra. Every other deep space mission, from lunar orbiters to probes at Jupiter, continued to report without interruption. Solar weather reports from NOAA and ESA's Space Environment Services confirmed a period of calm, no coronal mass ejections, no solar flares, no spikes in proton flux to account for radio disruptions. Inside mission operations, the language was less polished. An internal JPL memo, later leaked, described the blackout as statistically unprecedented and flagged the timing as highly coincident with external photometric events. When pressed in a teleconference, the NASA spokesperson sidestepped questions about 3Pi/Atlas, stating only, "We do not speculate on causes unrelated to standard mission risk." Meanwhile, independent astronomers published open letters demanding transparency, citing the precise overlap between the blackout window and the comet's closest approach to Mars's orbital path. The official narrative, stripped of detail and hedged in legal caution, offered little comfort. For those tracking the data, the silence felt less like a glitch and more like a warning. On February 18, 2025, 6 NASA and ESA Mars missions went silent within 10 minutes of 3I/Atlas entering Mars's orbital corridor. Deep Space Network logs confirm no hardware faults, and official solar weather reports show calm conditions during the blackout. Ground telescopes recorded rhythmic brightness pulses from 3I/Atlas, each coinciding with communication dropouts. No other deep space missions were affected, and the Vera Rubin Observatory detected 3 companion objects maintaining fixed formation with the comet for 48 hours. Despite these documented anomalies, agencies have offered only statements citing a temporary anomaly or engineering issue. As of today, the precise mechanism behind the disruption remains unverified. The blackout left critical gaps in Mars's atmospheric and surface data, underscoring the vulnerability of interplanetary science to sudden external interference. The facts are clear. The Mars silence began as 3I/Atlas drew near, but the true cause and its implications for future missions are still unknown.